Before we begin, we'd like to familiarize with the wave terminology. Here we have a wave crest and wave trough. The distance between two successive wave crests or wave trough is known as the wavelength. And typically, the time it takes for the wave crest to move from one position to the other position is the wave period. Now, the vertical displacement between the wave crest and the wave trough is known as the wave height, and half of that is known as the wave amplitude. From the equilibrium position, which is known as the still water level, we derive the water depth from the sea bottom, and here we have the crest region and the trough region, whereby for a sinusoidal wave profile, the typical wave crest and wave trough region will be identical. Now we note that the wave height, wavelength, and also wave period or wind waves are governed by the water depth, the fetch, duration, wind speed, and also the decay distance, which we will discuss in more detail later on. So these are the definitions of the wave terminology. More specifically, we want to look at wave steepness. Wave steepness is the ratio of wave height to wavelength, h over L. Now, if you recall the small amplitude wave theory, it means that the wave height must be small compared to the wavelength. Also, we want to define what we mean by wave speed. Wave speed is the velocity with which the waves travel, which also is known as a wave celerity. And finally, wave group is a long sequence of similar waves traveling together in the same direction. Next, we want to familiarize ourselves with the mathematical representation of the small amplitude wave theory. Here we are looking at a surface monochromatic wave. Monochromatic means that the wave is made up of a single wave spectrum with only one wave period and so one frequency. And here we see the profile of the wave, which is sinusoidal. We have a crest, a trough, followed by a crest. So we have a wavelength represented by the notation L, and wave height represented by the notation H, and the wave is propagating at a wave celerity C. Now, if the water is undisturbed, we will have a still water level, or SWL. The displacement of the water surface profile from the still water level is represented using the notation eta, and so eta is always changing at every point and also at every time. Now, the water depth is defined as the distance from the still water level to the seabed, and here we have a vertical axis marked as z, whereby it is 0 at the still water level and is positive upwards, so that it is always negative downwards, and that means it is always negative in the water column. Now, at any position, we will be marking it as d plus z. Remember that z is always negative inside the water column, so d plus z is essentially d minus the distance over here, so d plus z refers to any position in the water column. Now here we mark a typical equilibrium position, so that during the wave motion, the water particle will be in orbital motion around this equilibrium position. So the orbital motion will be the largest near the surface, and it diminish as we go further into the water column. So for a particle that is in motion, it always has a component of velocity in the direction of wave propagation u and another component of velocity in the vertical direction w. So a particle will typically be moving forward at the crest, is typically moving upwards at the still water line here. It's moving backwards at the trough, moving downwards at the still water line here, and moving forward again at the crest, so that we have a orbital motion in a clockwise direction if the wave is propagating towards the right. Now, since the particle is orbiting around an equilibrium position, then the particle is said to be displaced a certain distance away from the equilibrium position. So the displacement from the equilibrium position also is made up of two components in the direction of propagation and also in the vertical direction. A sinusoidal wave profile can be described by an equation like this, so that the vertical water surface displacement eta is equal to h over 2 times cosine of 2 pi x over L minus 2 pi t over t, right? You notice that we use cosine here, but basically the profile we see is sinusoidal. Now, if the cosine function equals to 1, then this whole expression is not important anymore. Eta then equals to h over 2. H over 2 basically is the amplitude of the wave. So when we are looking at the wave crest, cosine equals to 1, so that eta equals to the wave amplitude and is positive. But when we are looking at the wave trough, the cosine function equals to -1 and eta equals to -a. Still the amplitude, but is now negative. That means it has moved downwards. The surface of water has moved downwards. Basically, h is equals to 2a. A is the amplitude. Now, the function inside this cosine expression is the phase angle. It depends on the position x, and it also depends on the time t. 2 pi over L is the wave number as before, k. 2 pi over t is the wave angular frequency, omega, as before. So at different location and at different time, the cosine function will keep on changing between +1, the maximum, and -1, the minimum, right? So that the water surface displacement eta at any location at any time is always changing, but it will never exceed +a or -a, the amplitude of the wave. On the previous slide, we have the equation for the water surface displacement given by eta. Here on this slide, we have the equations for the water particle displacement given by c in the horizontal direction and zeta in the vertical direction. Now, the equation have a very similar structure, whereby this part is the magnitude, the maximum, and we have a phase angle which depends on x and t, k and omega. But for water particle displacement, we have this additional term here, which is the hyperbolic function, whereby in this part it depends on z plus d, and as mentioned earlier on, z plus d is the location in the water column from the seabed. So the horizontal and the vertical displacement is different at different point in the water column. Now we come to local fluid velocity. Now this is the first time we use the term velocity. remember previously we have been talking about the wave celerity c equals to L over t. That is how fast the wave is moving. But now we're talking about how fast the local fluid particle is moving, and that is called the local fluid velocity, and is different from wave celerity. Here we're talking about how fast the individual particle is moving in the orbital motion. So we have the horizontal velocity u and the vertical velocity w. We have similar structure here, the magnitude for a deep water condition. This is how fast the velocity in deep water condition. When it moves into shallow water region, when the vertical component becomes important, the z plus t becomes important, then we have the hyperbolic term. And of course, as the particle move in the orbital motion at any location at any time, the phase term will always be changing. Okay, so this gives us the velocity component of the fluid particle, which is different from the celerity of the wave. And since the fluid particle is moving in an orbital motion and is keep changing direction, so it also has a local fluid acceleration term, the acceleration in the x direction and acceleration in the vertical direction, which has a similar form as the local fluid velocity. If we look at this plot, it shows us the water surface profile. Remember again that the displacement of the surface water profile from the still water level is eta, and for the particle motion, it will have the horizontal displacement given by c and vertical displacement given by zeta. Now, as the wave propagates, the velocity of the water particle keep changing. When it is at the crest, it will have a net positive velocity for u, but a zero velocity in the vertical direction because it cannot go any further up. When it comes to this point over here, okay, the velocity of the water particle is actually moving up. That means the next moment, this point will be going upwards because the wave is moving in the rightwards direction. And if the water particle is at the lowest point, it will be moving backwards the next moment. It has no vertical velocity component, and so on and so forth. And likewise in terms of the acceleration, which is basically out of phase. You notice that if the velocity is forward, the acceleration is actually downwards. If the velocity is upwards, the acceleration is actually forward. The phase difference is always 90 degrees. Let's look at an example here. We have a wave in water 100 meter deep with a period of 10 seconds and a wave height of 2 meter. Determine the wave celerity, wave length, and wave steepness. It then asks what is the water particle speed at the wave crest. Alright, we want to determine the wave celerity and also the wave length. They are closely related because c equals to L over t and t is a constant. T equals to 10 seconds here. So in the solution here, we notice that we have, first and foremost, we do not know whether this is deep water, shallow water, or transitional water, but we can make an assumption. Let's say we assume this is a deep water wave, and that would means that the deep water wavelength L0 should equals to gt squared over 2 pi. So if we solve that, we get the wavelength of 156 meter. We can check the relative depth DOL. If the water depth is 100 meter and the wavelength is 156 meter, then we get DOL that is greater than 0.5. That confirms that this is a deep water wave, so we are correct. And based on this, we then conclude that the wavelength is 156 meter. But we can also apply the general equation L equals to GT squared over 2 pi times tangent hyperbolic 2 pi DOL and do it by trial and error. We should be able to arrive at the same answer. The wavelength is 156 meter. After we have obtained the wave length, now in order to get the wave celerity, we just need to compute it as L over T, so we get the wave celerity as 15.6 meter per second, and whereas for the wave steepness, it is the wave height h over the wavelength L, so we get the solution as 0.013. Next, the equation asks for the water particle velocity at the crest. Now we recall that this is deep water, and also the general expression for water particle velocity U is equals to this, whereas W must be equal to 0 at the crest. So we do not need to solve this component. So now let's look at this expression. Now since we are solving for the water particle velocity at the crest, so that means this hyperbolic term is not important because this only is required if we are interested to solve any other position inside the water column. Because right now at the water surface, okay, z is equals to 0, so basically the numerator and the denominator is the same, so this whole thing equals to 1. This cancel off. And also since we are solving for the water particle velocity without any specific location or time, so the base term is not important to us, so we are left with only the deep water term here. Now the right hand side looks like this. Since it is the deep water term, that means the L must equals to L naught, and we know that L naught equals to GT squared over 2 pi on the previous slide, so we can simplify that to pi h over t, so that's where we solve and obtain the water particle velocity at the crest equals to 0.63 meter per second. In this next example, we're actually looking at the same wave in a water 100 meter deep with a period of 10 seconds and a height of 2 meter, but which has propagated to a water depth of 30 meter. So now what we are going to do is that we want to determine the wavelength and the wave celerity. In this case, we again do not know whether this is a deep water, transitional water, or shallow water condition, but we can use the general expression, which is always applicable. Alright, and if we solve by trial and error, then we get the wavelength, which now has reduced to 137 meter. Now as the wave propagates from deep water to shallow water region, remember the wavelength reduces. In a way, you can imagine that the wave is being squashed and becomes shorter and shorter because of energy concentration. But at the same time, when this wave move to the shallow water region, they are also increasing in wave height because of the wave concentration. So they become shorter, they become higher due to the energy concentration. Alright, we want to check the relative depth DOL. We found that that equals to 0.2. So we confirm that yes, indeed, this wave is now in the transition zone. And so if we want to find the wave celerity, which basically is LOT, now we get it as 13.7 meter per second. Now what if the same wave propagates further to a near shore region which is only 2.3 meter deep? We want to calculate the wave celerity and the wave length again. Now we know that in the shallow water region, the celerity C equals to square root of GD, and we calculate that, we get 4.75 meter per second, and the wavelength is equal to 47.5 meter. We check the relative depth DOL, indeed that is smaller than 0.05, and so the assumption of the shallow water condition is correct.